Okay, it says this hangout on the air is now live. We'll see if it records. And I'm wondering, do we have any questions or anything that you want to cover from yesterday's session or any of the other previous sessions?
I did have one thing. I missed last Thursday.
Yeah.
I was wondering if you could send that email to me again.
Yeah. I'm not sure that I sent it to everybody. I will send that to you. I may have missed sending it out, the link to everybody. But yeah, I'll send that link out. I'm going to send the link to all of them. The ones for session 5 and session 6, I'll send out this evening. And after session 7, I'll have that out in the morning, get that out to everyone. So my apologies for not getting that link to you, Cohen.
You might have. I get so many emails, it probably got buried somewhere.
No, I think I may have missed sending it out. I apologize. Just hasn't been a normal weekend for me after my surgery.
Oh, sure.
So at any rate. Okay. Hopefully Dave Criddle will join up with us here in a minute. Let me see if he got the link. You get link. Let me do a refresh here. Okay, good. I'll send that off.
I got your email.
Hey, there he is. Dave's in here. I don't know where Mitch is. But I'm going to go ahead and get started here. I already started the live broadcast and fiddling around, trying to get some of the technical issues sorted out and going and everything. We're going to be talking about modes tonight. Let me get Herman Munster off of here and start our slideshow. We're on the current slide. Everybody's got that. Everybody should see Chapter 4, Topic 13, Multi-Mode Radio Excitement. Ooh. If you look in your book, I think it's on page 119. Okay. We start there, and it shows a picture of a multi-mode radio that looks like the Kenwood 2000. And typically it has all the modes on it you need to communicate: single sideband, FM, CW, VHF, and even has UHF and some digital capability as well. And then we're going to look over here. We're going to talk a little bit about modulation. And on page 120 in the little blue Elmer box, it has a little diagram there, but I have other diagrams that I downloaded that will be available that I'll show up here as well. Kind of talk a little bit about the different modulation modes and that. Let me see. Let me show you. Let's see. Where is it? There it is. That right there is an ICOM 706 MK2G. And I have that little jewel right there. And it's a nice little compact, portable, basically mobile radio that covers all the HF bands, or most of the HF bands, along with VHF and UHF, and incorporates the various modes of operation: CW, single sideband, AM, FM, things of that sort, and has digital connections. That little box I showed you last evening, the little USB signal link, is what connects to this radio, between this radio and the computer, and allows me to operate digital as well as allow me to decode CW or Morse code signals directly off the air as well. Great little rig. I've had it in the shop one time. I bought this back in 2004, and it's been working great ever since. And right now, it's the only functional HF rig I have, or multi-mode rig that I have in the shack since my Kenwood 940S decided to take a nosedive. I think the PLL circuit in it has gone bad, but I'm not sure. And me being a one-arm paper hanger right now, I would find it very difficult to try to open it up and try to repair it. So if I can find somebody locally, or if I need to send it off to repair, I'll do that. I don't like being without at least 2 HF rigs. But any rate, there you go. Let's move along. So what is a transceiver? Anybody that's familiar with even CB, or even those little tiny FRS radios, pretty much should know what a transceiver is. And it's very straightforward. It's not an antenna switch, uh, and it's not a component in a repeater that filters out unwanted interference. It's not a type of antenna matching network. What it actually is a combination of transmitter and receiver. It combines the functions of both of those. And in the early days, I think I showed you my HT40 transmitter and my a picture of an SX140 receiver. I had separate transmitters and receivers as I got started into the hobby. So I didn't really have a transceiver, and except for a CB. That was the only thing I had that was a transceiver. And then I eventually bought my 2-meter rig, and then I upgraded my HF equipment to a Kenwood 520S, which is a hybrid transceiver. It has tube finals and solid state. Otherwise, it's solid state for all the rest of the stuff. Okay. Which type of voice mode is most often used for long distance or weak signal contacts on the VHF and UHF bands? Be kind of careful with this. Uh, Mostly, we know that on HF, we use a particular type of modulation. And if you're familiar with CB came out, initially they were AM radios. They had 23 channels. They eventually went to 40 channels. And then when they brought out single sideband capability on these radios, the manufacturers were advertising, "Oh, look at this. It's not a 40 channel radio. It's a 120 channel radio." Well, that was kind of a misnomer. But in a way, it did have, if you wanted to count it that way, 120 channels. It had 40 AM channels, and it had 40 lower sideband channels. It had 40 upper sideband channels, but these were all pretty much shared frequencies. So, and it also kind of showed that, well, here you go, on sideband, you can transmit 12 watts instead of the 4 watts. Well, there's a reason for that. And it's still the same power. It's just that how they configure the power as it transmits and where it concentrates kind of gives you a 12-watt ERP, or effective input to your antenna. So, but at any rate, the voice mode commonly used for weak signal on VHF and UHF is single sideband. And that was kind of a rarity back in the day, and I almost wish I had a single sideband rig back then. I have that capability now. I have talked on 2 meters and UHF single sideband, and it's quite interesting. I have a beam antenna up here, and I was able to talk on 2 meter sideband direct to a station almost in Fredericksburg, Virginia. And it's how that operates that gives you the distance that you want or need to communicate directly without a repeater and without using FM. Specifically, 6 meters is kind of a VHF low band frequency, and they're ideal for bouncing off the ionosphere. 6 meters is also considered what they call the magic band. I tell you, when the band openings occur on 6 meters, you can get some phenomenal distances on 6 meters. And you definitely want to be operating single sideband when you do that. All right, on page 120, it shows a little bit about the modulation here. Your transceiver can send and receive different modes of radio signals, and the mode refers to the type of modulation or the emission used to send signals. And you look at the diagram there, you see an information signal or a modulating audio wave, and as it goes through the time there, that's the first diagram there. That would be your audio, what you're talking or what you're saying. And then below below that, you see what is the carrier frequency. It's an unmodulated frequency. So if you just keyed up your microphone and you looked at your oscilloscope or some other instrument that can pick that up, you see that frequency there. That's just a frequency, and it's unmodulated. It's a dead carrier, and there's no intelligence or intelligible information on that. But if you put that audio signal in the top portion here, and applied it to this dead carrier, you then modulate, or you'd have what's called an AM signal or an amplitude modulated signal. And you can see that in this third diagram, as a person talks, the amplitude varies on that signal. The amplitude of the signal varies. So there's highs and lows, and it rises and falls. Conversely, when you're modulating an FM signal, it actually changes the frequency of the signal, so that it's not a dead carrier frequency, but it's actually changing it within a few kilohertz of your carrier frequency. And that the width of that, of course, is, if you remember back before, for an FM signal is 10 to 15 kilohertz, typically. Let's see. I have, where is it? Some technical info here. Let me bring this up. There's the difference between a modulated AM carrier and a modulated FM carrier. And you see that it changes in amplitude for the AM. The amplitude remains constant, but the frequency changes as you're talking with that signal. What else do we have here? Okay, it's can I get this on? I can't get it on. Okay, never mind. It won't work, that one. Well. Okay, I can't get the other signal on. Well, moving right along, any questions on FM, AM, single sideband? We're going to get a little bit more into that. Oops, there it is. Of course, I've opened enough of them here. Okay, forget that one. That's not right. Okay, let's move along, and if there's no questions, and gee whiz, come on now. There we go. All right, what is an advantage of single sideband over FM for voice transmissions? Now, there's a particular width that a signal will occupy based on the mode of modulation that you use. And so the primary advantage of a single sideband over FM is that the single sideband definitely has a narrower bandwidth. We use frequency modulation through FM repeaters, but near the bottom of 6 meters, 2 meters, 1 1/4, and other bands, we use single sideband, which uses a lot less bandwidth than FM signals. So C is the proper answer. Single sideband is much more narrow. a typical AM transmission, which contains your carrier frequency as well as the upper and lower sideband portions of the modulated signal, is approximately 5 to 6 kilohertz in width total, versus the FM, which is much wider, typically of 10 to 15. And then your single sideband of that signal is even less than the AM. So it's like half of the AM signal. Let's see. I had another. See if I can find what I'm looking for here. This gives a little bit better indication of an AM signal versus FM. And you see the carrier wave and the amplitude modulation varies in amplitude, but the frequency is constant. Whereas with the FM side, when you modulate it, the amplitude is constant, but the frequency varies. That's how you tell the difference between FM and AM. AM is a constant frequency, amplitude varies. FM is amplitude is constant, but the frequency varies. Okay, what is the function of the single sideband CW FM switch on a VHF power amplifier? And that is on the bottom of page 120. It kind of gives you a little bit more information than what the slide is going to show you here. But it's to set the amplifier for proper operation in the selected mode. If you're going to do AM, you're going to have a switch that will select AM. Another one, that same switch, if you're going to use FM, you can switch it to FM. So basically, most modern VHF external power amplifiers can be switched between linear and Class C for the appropriate mode, depending on what you're using. I think we might get into Class C amplifiers a little bit later on. Just know that right now, for the purposes of this question, that switch is to set the amplifier to proper operation in the selected mode. Where am I here? Okay. Which of the following is a form of amplitude modulation? And there's only one answer to this, okay? And that's answer C, because single sideband is a type of amplitude modulation. However, it is more efficient, and it is a modified form of amplitude modulation. The components, let's see, I think I have that information up here somewhere that shows the components between, here it is. There it is. Okay. This is your typical AM signal, and it shows basically the bandwidth. In this case, your carrier frequency is 28.4 megahertz, and the bandwidth operates from 28,397 to 28,403. Contained in those, between the 397 and the 400, is the lower sideband signal, and you see where the carrier frequency is here. That remains constant on 28.4, and the bandwidth is not the varying of the frequency. It's just the amount of space that signal occupies on the band. You're still varying the amplitude, but it's occupying a certain amount of space on that channel. And you see that you have a component which on one side is lower sideband and the other side is upper sideband. And if you take away your carrier frequency and you take away one of the sidebands, in this case, you take away the lower sideband, you're going to transmit just on the upper sideband. And you can see that it's a much more narrow. In this case, it's only taking up 3 kilohertz of bandwidth, and all the information and all the power that's going into that signal is going into the upper sideband modulated signal. There is no carrier. The carrier, through the magic of electronics, is taken out. Once the signal is modulated, it's taken out, and all you have is this intelligible, or you hope it's intelligible, signal going out over the airwaves. So that's kind of the relationship between the carrier, lower, and upper sideband. Any questions on that? Okay. That just kind of represents how more efficient a single sideband signal is. A single sideband is again, the information that I just showed you here. Let me see if I can bring that up. Okay. Uh, when you're doing amplitude modulation, there is a generation of information that's injected into the signal. When you key that microphone, you have an upper component and you have a lower component, and these are called sidebands. And the upper component, let me bring up this other diagram that might give you a little bit better idea of what a sideband is. You have your fundamental carrier center frequency, and you see that there is a certain bandwidth assigned around that. This is why, let's go to the CB, for instance. CB is channelized, and those channels are approximately 10 kilohertz apart. And that's to accommodate the 5 kilohertz on either side of the frequency for that particular channel. And if you've heard of bleed over, okay, that was a term that a lot of CBers used back in the day. Is somebody's bleeding over on me, and I didn't hear that, blah 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 blah. And what is happening is that one side of that information, let's say you're on channel 10 and somebody is on channel 11 and they're bleeding over on to you on channel 10, they're close enough to bleed. Their bandwidth is going outside the normal bandwidth of the pass band of the signal. I don't want to get too technical here because it's not really relevant to passing the test. But I want to try to explain it in lay terms the best I can here. But the lower sideband of channel 11 is bleeding over onto the upper portion of channel 10, and it's kind of messing up your receivability. If you look here at this here in the red, it says the RF bandwidth of a given AM signal is twice that of its audio bandwidth, which is unlike single sideband where RF and AF bandwidths are equal. So you see here that there's the upper sideband is just the other half of the intelligence that you're transmitting out on that carrier. I'm not sure if I'm describing it properly or not. It's a component of your signal that's basically duplicated in essence from one side to the other. You can eliminate one and still talk. That's the modulated portion of your transmission. That's what a sideband is. It is a modulated portion of your transmitted signal. You key the mic, this is all you have right here. You have this little line right in the middle. That's your carrier frequency. And then you talk, and the information contained in what you're transmitting is the sideband, either upper or lower. I don't know. Does that help, Jonathan? Can unmute your mic if you want.
Okay. Yeah, what is the sideband? Is that just part of the wave?
What I was saying is that you're gonna have to mute your mic here. It's the intelligence. Let's see. I wish I could take control of this. It's the intelligence. It's what you're talking. It's what you're saying. It's your words. It's the information is contained in that sideband. I don't know how else I can describe it to you.
Go ahead.
If I may,
Yeah.
channel 10 has the channel, and then you have the upper side and the lower side. So you actually have three modes of transmission and receive there.
Right.
Is that correct?
That is correct.
Okay. Thank you.
So when you talk about the sideband, is that just part of the wave that's being utilized to transmit the information?
Yes. If you see the diagram, that's your wave.
Okay.
Yeah. Right there. If we were to look at it at a different, let's see if I can find another graphic here that might help. All right, let's see. Let's try this. Yeah, this is just part of the spectrum. If you ever get down into the technical nitty-gritty of all this, if you really want to get that technical, there's loads of information that can describe it to you much better available out there on the internet. But the sideband is generated when you modulate that carrier. The sidebands are what's generated as part of that wave that is going out off of your transmitter to the rest of the world. And it just happens to be two components. The one component on one side is upper sideband. It's on the upper side of your carrier frequency. And the other component is the lower sideband on the lower side of your transmit frequency. And that is the intelligence or the information portion of your signal going out. That is the modulated portion that is being piggybacked on the carrier frequency. I'm going to do this. Here is a link I'm going to throw in there. This is at Wikipedia that might help you a little bit if you wanted to look at that a little bit more in depth. But by and large, again, I don't want to get too technical. We want to try to get you passed and licensed and everything. So just know that there are intricacies that are out there in the technical aspect that is part of your learning afterwards. And right now, just know that the single sideband is much more efficient than AM. Okay, which sideband is normally used for 10-meter HF, VHF, and UHF single sideband communications? Now, there is a standard that has been set aside as far as which sideband to use, depending on what band you're using on the ham radio bands. You're going to be using the tech, since having a tech class license, unless you go to general. The lower frequencies for 160 meters, 80 meters, 40 meters, those are all lower sideband. And most transceivers will automatically, once you switch to that band, will automatically switch the modulation or the mode to lower sideband. When you get to 20 meters, and on up 20, 15, 10, VHF, UHF, the convention is upper sideband. So again, most of the modern rigs will automatically switch to the proper sideband to use for that particular band that you're on. But we always use upper sideband as our communications mode for VHF and UHF by convention. Let's see, which of the following describes combining speech with an RF carrier signal? Well, we've been talking about this. Not too hard to figure out, but your answer is C, modulation. It's the process of applying information, be it voice, video, or digital, onto a radio signal. When you transmit, you modulate. You create sidebands, upper sideband and lower sideband, particularly when you're doing amplitude modulation. So modulation is the methodology of applying information or speech to an RF carrier. So the approximate bandwidth of a single sideband voice signal typically is B, or 3 kilohertz. If we go back to the other diagram that I had there, you see, again, your carrier frequency is 28.4 megahertz. In this case, it has frequency in hertz. And the upper portion, or the bandwidth of that side of the conversation, is at 28.403, or 3 kilohertz. Total bandwidth of that AM signal is 6 kilohertz. So when applying that, the single sideband, whether it be lower or upper, and if it's a properly adjusted transmitter, even for VHF or UHF, it occupies approximately 3 kilohertz of bandwidth. Okay, which of the following is an appropriate receive filter bandwidth for minimizing noise and interference for single sideband reception? A lot of rigs come with filtering already built into them. And most of them really have this kind of filtering already built in, but you can get some that are a little bit more narrow. But for single sideband, the 2400 hertz filter automatically clicks in. And that's within the 3 kilohertz or 3000 hertz bandwidth that you would have for a single sideband reception. And that kind of prevents, from adjacent channel interference. It kind of minimizes that from coming in on the side, because it says, okay, my receiver is only going to receive a signal that's 2400 hertz or 2.4 kilohertz in width. Where may single sideband phone be used in amateur bands above 50 megahertz? Yeah, this is kind of an interesting one here. And remember what I said yesterday, there is a restriction on the very, very low end of 2 meters and 6 meters, being 50 to 50.1 and 144 to 144.1, strictly reserved for Morse code or CW. But beyond that, you have the ability to broadcast single sideband in at least some portion of all the amateur bands above 50 megahertz. You'll learn some of the conventions a little later on, and if you look at your chart, that chart that you had, it does give you an indication. Let me see if I can find it here. Well, by gum, there it is. Bring this up here. You can see that according to the color code here, and we're going to go ahead and pick on 2 meters and 6 meters. You can see CW and weak signal, no FM, and those portions there that are marked in red. But then you have a portion of 2 meters that says no FM, but you can do single sideband. And then pretty much the rest of 2 meters from there on is reserved for various types of modes like satellite operation, or FM repeater or FM simplex, uh, throughout the rest of that. So there is some portion of these bands in which you can operate single sideband. You see it here in the 222 and the 440 band. It shows where you can operate single sideband, and that's marked by the white area. And you see those here too. So while you're not really restricted to just FM on 2 meters, you do see here that there is a portion that you can really use single sideband anywhere in there if you really wanted to. But by gentleman's agreement, we kind of restrict single sideband down to particular portions of each band. So the correct answer is at least some portion of all these bands. There it is. Alrighty. So which of the following controls could be used if the voice pitch of a single sideband signal seems too high or low? There are controls on your transceiver, particularly the receive side, that if you're not hearing it properly, let's say you're on frequency, but somebody's not quite on frequency, rather than change your transmit frequency, there is something called a RIT, or a receiver incremental tuner, or clarifier. It's called clarifier in CB, but it's a receiver incremental tuning. It actually shifts the IF signal internally so that you can clear up the received signal so that they sound pretty much normal without changing your transmit frequency and messing it up on the other end. So that's what you're using, the RIT or the clarifier. What does the term RIT mean? Well, I think I already said that. It simply means receiver incremental tuning control. Answer is B. So what is the name of a circuit that generates a signal at a specific frequency? Well, it's actually the smallest answer, oscillator. It oscillates back and forth and actually creates the signal that you would transmit out if you were to do a dead carrier. The oscillator is actually what generates the signal going out. That's your dead carrier once you key the microphone. And then you modulate that oscillator, and that's where you get your AM signal or double sideband, which contains both your lower and upper sideband information. Which of the following types of emission has the narrowest bandwidth? Boy, this one's pretty easy, really, when you get right down to it. One of the most efficient signals you can use is CW, or Morse code. It contains the most narrow bandwidth you can possibly use. That is why when you look at those that chart there, let's see if I can bring it back up. When you look at the chart here, you only have 144.1 to 144.3. That's only 2 kilohertz, 200 kilohertz of space available for single sideband, but you only have 100 kilohertz for CW. But within that 100 kilohertz, you can get 10, 12, 20 CW signals going. Such a narrow bandwidth, and it's not used very often anyway. But actually, CW is the most narrow bandwidth of all the modes. So what is the approximate bandwidth required to transmit a CW signal? And again, in your book, it kind of shows you there that it's 150 hertz. So it's not very wide. Not very wide at all. When you switch your multi-mode rig over to CW, you'll see that the bandwidth narrows, and this minimizes interference from other CW signals off frequency. So on transmit, 150 hertz is about right. Actually, they can be a little bit more narrow, but your answer is B here. Which of the following is an appropriate receive filter bandwidth for minimizing noise and interference for CW reception? 500 hertz. Now you can get them again more narrow than that, but 500 hertz is a common filter to kind of narrow your receive bandwidth and reject adjacent frequencies from interference on your receiver. 500 is typical. So what is the advantage of having multiple receive bandwidth choices on a multi-mode transceiver? This is kind of an interesting question in and of itself. The different choices that you have will allow you to reduce your noise and interference by selecting a bandwidth matching the mode that you're going to be using. And some radios, they come with standard filters. Most radios do, but other radios have additional filters that you can actually install on them. I have on my 706, I can install some additional filters if I want to narrow the bandwidth on the receive side even more than what I have right now. And all that does is really reject any other signals on either side of my receive frequency, so that I'm more likely to hear the person that I want to hear and reject everything outside that particular bandwidth. So you want to select the proper filter when changing modes to tighten up or expand your filter selection. Which term describes the ability of a receiver to detect the presence of a signal? There is an ability for that receiver, and you kind of see this when you look at the tech specs of any radio. It has a particular indicator in there that says this is the ability for this receiver. In other words, how sensitive is it? Okay, is sensitivity the ability to receive or detect the presence of a signal, and especially if it's a weak radio signal. So B is your answer here, sensitivity. Which of the following is used to convert a radio signal from one frequency to another? This is another interesting aspect of ham radio, because some radios, some of the HF radios in particular, had other auxiliary equipment that you could buy in order to utilize bands that aren't typically on your HF rig. In this case, you're using a mixer, which is a nonlinear device that takes two radio signals, creates both the sum and difference of the frequencies of the two input frequencies. So you're mixing that signal. You're mixing several signals to create another signal. Answer is B on this. Which term describes the ability of a receiver to discriminate between multiple signals? This is a little bit different than sensitivity. You want to be able to basically pull out only the desired signal that you want to receive, and that has to do with selectivity. How selective is it? Is it selective enough that it will reject the side? This is where your filtering comes in. So it's the capability of a radio to specifically hear one frequency and discriminate against signals on either side of that frequency. Selectivity is the correct answer. How selective is it? How sensitive is it to actually pick up the signal? How selective is it to actually bring in the signal that you want to hear and reject others? So what is the function of automatic gain control, or AGC? Well, that helps your audio or relative to make sure that it's relatively constant and it's always working so that you don't have a lot of fading and some highs or loudness, and then it goes soft. So your automatic gain control kind of helps let that audio or the volume be as constant as possible and not go through huge variations. Automatic gain control. Exactly what it says. Where is an RF preamplifier installed? Now, this is a preamplifier. And of course, the preamplifier is not on the transmit side, but it's the preamplifier's function basically is to help pull in a weaker signal and amplify it into your radio. So your preamplifier would typically go between your antenna and your receiver. I have, I don't know if you're familiar with, TV head-end equipment. You have an antenna, and then you have a distribution point inside that receives the TV signals. And some of those signals are a little bit weak. And when you put it through the distribution node in your home or business or wherever it is, I have a distribution setup where I can receive TV off the air and distribute it throughout the house to different places. But if it's a weak signal, it doesn't get distributed out because through the loss of your splitters and combiners and your coax and things of that sort, really requires a preamplifier to boost that signal, takes that weak signal, it increases it, it boosts it before it actually sends it out to the TVs and the rest of the house. So, what device converts the RF input and output of a transceiver to another band? There is a device that converts the RF input and output of a transceiver to another band. This is a little bit different from the mixer that we had before. Um, and if you want to review that, we can go back to that if you'd like. Let's see where it is. If I can find it here. Oh, where was it? There it is. T7A3. All right. I'm not going to mess it up. At any rate, the following is used to convert a radio signal. If you go back on your in your book there and look again, let's see what page it is. I think T7A03. I think that's on page 123. Is it? There it is. Page 126. Okay. T7A03, which is used to convert a radio signal from one frequency to another. Your answer is B. So you're converting a radio signal from one frequency to another. This one is converting the RF input and output of a transceiver to another band. And the correct answer to that, let me get this up here again. Oops. There it is in a transverter. You use a transverter to convert signals from one band to another. Some of the HF rigs that I was talking about earlier, if you wanted to operate 2-meter sideband, let's say, you could put a 2-meter transverter or even a 6-meter transverter. There were hookups on some radios that you could put a transverter on and actually convert that to a 2-meter or 6-meter signal. And that's for that particular band. And that's what a transverter does. Any questions? Everybody okay with that? Which of the following best describes DMR or digital mobile radio? It's a lot of fun. I just wish I could use it more and knew more about it. At any rate, DMR or digital mobile radio is a technique for time multiplexing two digital voice signals on a single 12.5 kilohertz repeater channel. That's one of the advantages of DMR because you can have two signals simultaneously on a single repeater frequency. So, and it's called time multiplexing. And that's an advantage that DMR has. And it's one of the best descriptions of digital mobile radio is that you can time multiplex and share a channel by chopping the signal into time slots. What is a talk group on a DMR digital repeater? Okay, a talk group basically is a way for groups of users to share a channel at different times without being heard by other users on the channel. And there's a lot to this, and I'm not even going to get into it. The person that really has a little bit of know-how in this or has more know-how than I do is Kevin, W3XOX. And he can explain that a little bit more in detail. But basically, you're going to set up your talk group on your DMR radio so that you're only wanting to hear transmissions in that particular talk group, be it a local talk group or a worldwide talk group or a regional talk group. And that way, you know, people can talk without being aware of the other person if they're on a different talk group. You can be on this repeater here in a local talk group, while simultaneously there's people talking to other people worldwide in the worldwide talk group. At least that's how I understand it. Oops, what did I just drop? Not sure what I just dropped. All right. How can you join a digital repeater's talk group? Well, one of the easiest ways is actually just program your radio with the group's ID or the code. And this will automatically route the packets associated with that group to reach your radio and vice versa. So I have on the same frequency 3 talk groups set up. One talk group is for local and attack frequency. Another one is attack frequency along with a Pennsylvania-wide talk group. And another channel is programmed with a worldwide talk group. So although it's the same frequency, all I have to do is change to one of those depending on what I want to, who I want to talk to or what talk group I want to be a part of. It's one of those things that is better hands-on and shown in a workshop, basically. All right, which of the following best describes broadband hamnet, also referred to as a high-speed multimedia network? This is always fun, but you know, a lot of people are kind of into this Wi-Fi thing and this mesh network and things like that. But it's an amateur radio-based data network using commercial Wi-Fi gear with modified firmware. So, and it allows hams in some regions to build a shadow amateur radio-based data network totally independent of the commercial infrastructure. And it's just like having a ham radio internet, basically. So whatever's on the ham radio internet is what you have access to. And that's your broadband hamnet. I think Tom's into that pretty heavy, aren't you, Tom? Or at least you were at one time, I thought. Still with us, Tom?
Yeah, I'm there now. Yeah, it's kind of neat because you can send webcam video back and forth. You can hook up IP telephones with it. You can do file servers and send computer data. Anything that you would do over the internet, you can do over Hamnet, and you can do it with your own private network. So the mountainous area here makes it a little challenging, but there's a bunch of people doing it.
Yeah, I guess so. I'm not one of them, although I do have one of the Linksys routers, I think, that is capable of having the Hamnet firmware installed on it. And I'm willing to give it up if somebody wants it. Okay, where are we here? All right, that kind of wraps up the multi-mode portion of tonight's lesson. Are there any questions that anyone would like to ask? Anything you want to recover? It's not really necessary to have a total understanding of all these modes, but just to know that there are different modes, there's different capabilities, there's particular nuances of the different modes, and to know what the answers are to pass your test. There is so much more to understanding the different modes that are available in amateur radio that it's impossible to cover in something like this. Again, this is part of your ongoing learning once you get licensed, that if you really want to know the technicalities, the deep, dark technicalities and everything you wanted to know about these different modes but were afraid to ask, that's your learning process after you get licensed. You can dig into it really deep into the into what happened, Cone? Lost him. Who'd you lose?
You cut out for like right after you started talking. All sound was shut down. I didn't hear a word he said.
Oh, am I still working? Am I working now?
Yeah, now it just for some reason, just as soon as you started talking, it just shut. My sound volume just cut right out.
Really?
Yeah,
Did everybody else hear me? Did you hear me, Tom?
Yeah, I heard you. There was no dropout.
Okay.
It might have just been mine. I don't know. I lost you right after.
Oh, that made me concerned because if I wasn't coming through on the recording, all of a sudden I disappear and oh, where is he?
Must have just been mine then.
All right. But thanks for letting me know that I need to know that if I drop out. But that is your, that's what you can do once you get licensed. Just kind of know the basics for now of what you need to know, and for the purposes of answering these questions. And we don't have to get really deeply technical in it. John, I know you and your group, you're the type that really wants to know, the nitty gritty of everything, and there's nothing wrong with that. But I don't want it to overwhelm anyone to the point where, it seems hopeless or anything. We want to just go ahead and kind of follow this book and utilize the information in the book the best we can. One of the things I did notice in here, if looking in here for that chapter on that topic, where is it here? There are pictures that kind of show filters. There's also some information there on the single sideband signals on page 122 there at the bottom. Kind of shows a little bit of the relationship of single sideband versus carrier versus upper and lower sideband. And then your RIT control picture over there on the page 123 would be very helpful. Take advantage of the ham hints. Those are the little blue Elmer squares that will kind of help you understand a little more about what they're talking about here in the book. That's why I like Gordon West's information here. And again, as you get through this, there are some website resources on page 130 that can help you gain a better understanding of all this. And it's not that you shouldn't have some kind of understanding. The more understanding you have, definitely will help you answer the questions for the exam and everything. But don't let it overwhelm you. Don't let it, occupy too much of your time and stuff. So with that, I think, let's see. I'm not sure. Let me see how long this is. 238, 48, 10. 20. Okay, we have 19 slides. I think we have some time to do this. It's already a quarter after, and I think we can run through this pretty quick if everybody wants to do that, or we can cut it short. I think we still have time and plenty of time with the sessions that are left to make sure that we cover everything appropriately. We'll get started here. It's already 8:15, and we'll go. So when you're looking at interference problems, and that starts on page 131. So what might be a problem if you receive a report that your audio signal through the repeater is distorted or unintelligible? And we run into this every once in a while. Somebody has problems, you have a hard time hearing them, and you're not exactly sure what's going on. But it could be various causes to the signal. I've heard people who are basically a little bit off frequency. Their transmitter, their IF, could be needs to be retuned. Also, the batteries could be running low, or sometimes you're in a bad location. But all these selections here are correct. At one time or another, it could, one of these could affect you. If you're using a portable radio and you're in a bad location and you can't be heard, you're just kind of in and out of the repeater and or noisy and things like that, simply moving a couple inches or maybe a foot or two in one direction might get you into that repeater full quieting. And that's all that's necessary. So what may happen if a transmitter is operated with the microphone gain set to high? And whoops, where are we here? Oops, there we go. All right. We hear this every once in a while that sometimes, and I am not a proponent of using power mics on an FM transmitter. And there is a particular bandwidth that an FM signal occupies. A lot of repeaters have a limiter set on that so that you don't go outside that particular pass band of that signal width, basically. And if you're using a power mic, or if you're talking too loud into even just a stock mic, what happens is that, again, FM frequency modulation varies the frequency. The amplitude stays constant, but the frequency varies. And if you're talking too loud, that frequency may very well actually slip outside the pass band of the receiver on the repeater, or even on the receiver of the other ham who's trying to receive you. And that can cause some distortion. So if it's operated with the microphone gain set too high, the output signal might become distorted. What can you do if you're told your FM handheld or mobile transceiver is over deviating? Deviation, that's the key word there, over deviating. How much that signal deviates is the bandwidth of the modulated signal. And if it over deviates, in other words, it deviates outside the pass band of the receiver, it will distort. So predominantly what you can do is you tell the person to talk further away or talk softer. Now, proper use of a microphone is not to talk directly into it, but actually talk across it. And that will almost assuredly help you keep from overmodulating or over deviating your signal and going outside the received passband and causing distortion. So it means there's too much modulation driving your signal beyond its normal bandwidth. Talk further away from the microphone. What might be the problem if a repeater user says your transmissions are breaking up on voice peaks? There again, those voice peaks are what's causing your frequency to increase beyond the passband of the modulated signal, or the receiver rather, and so you're talking too loudly. So if you talk softer, it will have less of a chance to over deviate or overmodulate, or go outside the received passband, and would minimize your distortion. So talking more quietly or moving your mouth a little further away from the microphone until people can understand you clearly. Which of the following would reduce ignition interference to a receiver? Ignition interference is really a common problem on many radios, and the ignition noise is basically a pulsating noise for the most part, and I'm sure you've heard it occasionally when you start up from a light. You hear this kind of a whine, but you also hear this kind of a ticking sound as well. And what it can help minimize that or eliminate it is you turn on a noise blanker. The noise blanker, I have a built-in one on my little mobile 706. So if I'm running HF in the car on trips or something, I do experience engine noise. Sometimes I get engine noise from adjacent vehicles, and all I have to do is turn the noise blanker on, and it just kind of quiets that down. Which of the following could be used to remove power line noise or ignition noise? This is a little bit different, but predominantly you want to use a noise blanker to get rid of your power line and ignition noise. Well, actually, it's the same thing pretty much. It's a repetitive pulse noise, and with high peak energy and low average energy, the noise blanker is best suited to remove this type of noise. It also highlights noise notch filter here. I don't know why that's highlighted, but your answer is B, really. Okay. That's weird. What is the source of high-pitched whine that varies with engine speed and a mobile transceiver's receive audio? Again, that is, your alternator. Basically, it's an alternator whine that is causing that noise. You can use DC filter chokes and alternator filters in series with the red wire 12-volt DC lead. My mobile rigs are connected directly to the battery. I don't pull them off the distribution or fuse box at all. All my power wires go directly to the battery itself, and both the negative and positive wires are filtered with ferrite coils, beads, donuts, for lack of a better word. And that'll help eliminate your alternator whine as well. So which of the following could you use to cure distorted audio caused by RF current on the shield of a microphone cable? You want to cure distorted audio caused by RF current on the shield of the microphone cable. This is outside interference that you might get, but it always helps to have some ferrite chokes around, and that'll help minimize or get rid of that obnoxious distorted audio. So Keep those on hand. Ferrite chokes will minimize RF currents. What should be the first step to resolve cable TV interference from your ham radio transmission? Nobody likes to have their TV interfered with. And I know it used to be a problem way back when cable TV and satellite TV came about and, more digital means of communication. The TV interference didn't seem to be really much of an issue anymore. However, one thing to really check if there is a problem on your TV is you got to make sure that all your coaxial connectors are installed properly. And this not only just the TV, but on your radio as well. If you have a loose connection, that could cause problems and experience some RF interference on your TV because of a loose connection. So make sure that all those connections are properly installed and tightened down so that they're not loose. But which of the following can cause radio frequency interference? Well, actually, all of these choices are correct. You can actually overload the front end of a receiver, harmonics, spurious emissions. All of these choices are correct, and they all lead to radio frequency interference, but there are ways to minimize or eliminate it. So what is a symptom of RF feedback in a transmitter or transceiver? A symptom of RF feedback in a transmitter or transceiver. There's a certain amount of RF feedback, and it's very distinct because you're going to hear reports of garbled or distorted or unintelligible voice transmissions. In this case, you're on 6 meters for the first time, and signal strength tests with hams a few miles away indicate that you have a strong signal, but your modulation or your voice is slightly garbled, and it's most likely caused by RF feedback between your antenna and the microphone. So you could be getting RF back into your system from leaky coax or improper shielding or filtering or improper connections. So which of the following is a common reason to use shielded wire? Shielded wire is always a good thing to have as long as you don't create ground loops. I'm not going to get into the technicalities of that, but shielded wire will prevent the coupling of unwanted signals to or from the wire. So you don't want a conductor to radiate or receive radio signals or other interference. And the use of shielding is often an effective solution. The most familiar shielded wire is coaxial cable. So, which of the following actions should you take if a neighbor tells you that your station's transmissions are interfering with their radio or TV reception? I just tell them to go get lost. I don't care. It's my hobby. No, that's not true. That is not proper ham radio etiquette, nor is it being friendly to your neighbors. But in actuality, you want to make sure that your station is functioning properly and that it does not cause interference to your own radio or television when it is tuned to the same channel. So your neighbor comes over and says, hey, I'm getting interference, and maybe you were on the radio. You want to make sure that you're not causing the same interference on your TV. If you're causing that interference on your TV, then you got a problem on the transmitter side and you want to do some filtering. However, if it's not occurring on your TV and it's only occurring on your neighbor's TV, it's always the neighborly and friendly thing to do to say, look, this is what I'm going to do. I'm going to go and I'm going to get a filtering system, a high pass filtering system. I'm going to put it right on the back side of your TV that will filter out my transmissions and only allow your TV transmissions to come through. So, any rate, those are some of the things you can do to make sure that your equipment is okay and you're not causing interference to other people. What would cause a broadcast AM or FM radio to receive an amateur radio transmission unintentionally? Ooh, boy. And that's happened on occasion as well. So it just means that the receiver is unable to reject strong signals outside the AM or FM band. A is your answer here. And it has to do with design defects in the consumer electronic device. More than likely, it's a Part 15 device that the FCC says, oh, that has to accept interference, but it cannot cause interference. But needless to say, you want to be a good neighbor and help a neighbor figure out what's causing and how to remedy it. Which of the following is a way to reduce or eliminate interference from an amateur transmitter to a nearby telephone? Something you want to say, Tom?
Yeah, I'll make a comment.
Okay.
If anybody sets up a new station and they start having problems with interference with neighbors, call Kevin. He is the ARRL technical person, and he and the radio club will help you resolve interference complaints with your neighbors. It is a touchy subject, and generally, if handled correctly, it can be done very nicely. I've been involved in several of them. The other person that can be your ally is the cable company or the phone company, depending on what device is receiving interference. But there's a lot that can be done, and these situations normally can be turned around quite easily, and angry neighbors can become good friends. So drag somebody in from the club that has some experience in the issue, and we'll help you solve problems.
There you go. Thank you very much, Tom. Appreciate it. I wasn't aware that Kevin was the technical guru for the club for that type of thing. Okay. Well, now I know. All right. Which of the following is a way to reduce or eliminate interference from an amateur transmitter to a nearby telephone? Oh, boy. I know people that have had issues with neighbors and telephone interference. That goes back a long time ago.
Well,
However, what's that? Go ahead.
just to give you one simple example, up at W3SO on Wapsie, we had interference where the radio signals were getting into the guy's stereo. And Marty and I went over and we looked at the back of the stereo, and the patch cables that went from his turntable to his amplifier were exactly a half a wavelength on 2 meters. All we did was cut the plugs off and shorten the wires by about 12 inches and put the connectors back on, and we solved the problem.
There you go.
But the cable was a resonant length of an antenna. It was actually acting as an antenna and not a cable at that point.
Well, how about that? I know in high school we had there was this one particular desk. We had I don't know, some kind of a study hall, study group, and this particular room was equipped with headsets and other electronics that were used for various purposes. And there was one station in particular that if you sat at, you could pick up the local radio station, and everybody tried to get in there ahead of time to hear that. And nobody wanted to report that as a problem. They wanted to sit there and listen to the music coming off of the FM station. So it was a lot of fun. All right. So at any rate, what really the answer to this question is you just need to put a simple RF filter on the telephone. Again, a snap-on ferrite choke can act as an RF filter on the corded telephone equipment. How can overload of a non-amateur radio or TV receiver by an amateur signal be reduced or eliminated? And we're talking about an overload here. Simple answer to this is you want to block the amateur signal with a filter at the antenna input of the affected receiver. I had mentioned earlier a high-pass filter would allow only the TV station signals to come in and reject the signals from the lower frequencies that are on HF or the amateur bands. There's just a lot of simple solutions to a lot of the interference problems. And it doesn't have to be very complex necessarily. And a lot of it's common sense. Which of the following can reduce overload to a VHF transceiver from a nearby FM broadcast station? Okay, you want to reduce the overload to a VHF transceiver from your nearby FM broadcast station. Well, here again, you want a band reject filter. You're taking a particular band, a segment of the RF spectrum, and saying, I want to reject this portion of the spectrum and only allow what I want to receive into my receiver. So to prevent that, you use a band reject filter. Answer is D. So what is a Part 15 device? I kind of alluded to that a little bit earlier, but predominantly it is an unlicensed device that may emit low-powered radio signals on frequencies used by a licensed service. They're unlicensed, and they may share frequencies, but they are prohibited from causing interference to other licensed devices, such as amateur radios. But conversely, they must accept any interference from duly licensed transmitters, amateur or otherwise. So a Part 15 device cannot cause interference, and it must it has to accept the fact that if it's interfered with, it is an unlicensed device, and you can do whatever you can to filter it, to mitigate the problem, but legally there's nothing really that you can do or need to do about it. So what should you do if something in a neighbor's home is causing harmful interference to your amateur station? Well, you definitely want to work with your neighbor to identify the offending device. And you want to go over and you want to politely inform your neighbor about the rules that prohibit the use of devices that cause interference. And you also want to check your station, make sure it meets the standards of good amateur practice. So all of these choices are correct. But, you know, it is kind of rare that you would encounter any RF interference from a neighbor's device or anything. But nonetheless, your modern microprocessor circuits and home electronics can do some interesting things over your radio receiver. So all these answers are correct. One of the latest things is that LED lighting can cause interference on your amateur transceiver. And fluorescent lighting can do it as well, but LED lighting does it. And simply turning off the LED light will cause the interference to go away. So that brings us to the end here for tonight. Thursday night, we'll talk about electrons going with the flow. We'll get a little bit into the electronics aspect of things. Again, this is not highly technical, but at any rate, do we have any questions that anybody would like to ask or anything to discuss? That little radio right there, that was my first radio. I think I showed this to you before. The IC215, crystal controlled. There is a simple CW transmitter. That's an oscillator circuit. We talked about oscillator circuits earlier. So that would be considered an oscillator circuit. Hey, making ham radio great again. That is a picture of me sitting with my station equipment. That is the radio that's on the Fritz. That is the 940S. That is a 520S right there, and it has a bad VFO, and I got to fix it. There's my 706 down there, and that was one of the club transceivers that somebody bought from the club. My amplifier is sitting right there. So there you go. All right, let me close that up. I'm going to stop sharing. And here I am. So how is everybody this evening? Did you get anything out of it? Everything go okay? Any more discussion? Good. Good. I appreciate Tom's input to the course. I've depended on him as an assistant. Appreciate it, Tom.
You're welcome. It's always fun to do it.
We're missing Mitch tonight, and I don't know who else we're missing, but everybody else is here. John, what about your group? Anything from your group that you want to talk about, or anything you want to say? Unmute your mic.
No, I don't think so. Is it necessary once you set up your base station to worry about standing wave ratio, or as long as you're within the dimensions? Well, a lot of the radios have a meter right on them, do they not?
Well, yeah, most of your modern ones do. And SWR is an important factor. You don't want to have or standing wave ratio that's out of whack. Most trans will shut down if they encounter problems with the reflected signal coming back from the antenna. So you want to have an efficient system. Your forward power versus your reverse power, that's your SWR, or standing wave ratio, that you need to be concerned with. Most transceivers will tolerate anything up to about a 2-to-1. Try to keep it below 1-to-5 if you can, but a good efficient antenna, properly tuned, will go a long way to minimizing any problems or effect that you have coming back to your transceiver.
Is it necessary? How do I put this? Somebody in the club will probably help us set that up. But whenever you key the mic and your standing wave ratio is off drastically, there's a possible chance to burn out the finals, correct?
If there's not an automatic shutdown circuit, that is correct.
Okay. Do all the radios of today have the automatic shutdown?
A lot of the modern transceivers do. They will have a built-in circuitry that will reduce the power going out to your finals, and thus protect them from burning out and overloading. But yeah, I mean, there's people here that in our club that have all the necessary test equipment to help you get set up and make sure that everything is set up properly and that it's operating properly and you're not having any problems. You'll find some modern transceivers, yeah, they have meters, they have built-in SWR meters. Some of them even have their own built-in antenna tuner.
All right, thank you.
Yep. Good deal. Cohen, anything from you? Your mic is
sure. I'm pretty good, actually.
okay. Real good. Real good. Good to have you along. Dave, what about you tonight? Anything? Good to go? All right. Well, with that, I'm going to go ahead and I'm going to stop the broadcast, and we're going to end